This is my presentation on Lab 3 to find the mass of a black hole. In this lab, we will be analyzing the path of a star around a black hole in order to find the force acting on the star, and then we'll use basic physics principles to estimate the mass of a black hole. We are interested in finding this answer because it will show us the relationship between force, mass, and momentum that controls the movement and behavior of heavenly bodies. To do this, I will first be deriving the equations to find momentum and eventually force, and once I have found force, we will use that information to find the mass of a black hole using Newton's law of universal gravitation. Then I will discuss my results and a few additional questions. And here's the information I was given: the gravitational constant, the mass of the star, that delta T is 1 day in seconds, and here is the model I was given based on my tech email. And based on the information I was given, I have chosen to use the momentum principle, Newton's second law, and Newton's law of universal gravitation. We have been given the mass of the star's path around the black hole, and its velocity, and with this information we can use the momentum principle shown below to find initial and final momentum. And here is a figure I made to show the direction of the momentum and the velocity, which are parallel, and how it is tangent to the path of the star around the black hole. And here is the model I made to determine momentum. You can see how I calculated velocity, and then I calculated momentum initial and final based on that velocity, and that is times the mass of the star, and also how I calculated delta V and delta P. And so Newton's second law tells us that force equals mass times acceleration. We also know that the definition of acceleration is delta V divided by delta T. And so we can swap that into Newton's second law to get our second equation here. And we also know that the momentum principle states that delta P equals mass times delta V, which we can also swap into our equation to get our final equation shown. And this simplifies to give us that F net equals the change in momentum divided by the change in time. Here you can see the model I made to show the directions of the new force. You can see that the perpendicular component is pointed inwards towards the center of the black hole, and the parallel component, which is also parallel to momentum, is tangent to the path of the star. And here's my model for determining force. You can see once again how I calculated delta V and delta P, and that F net equals delta P divided by delta T, and also how I calculated the parallel and perpendicular components of momentum. And now that we have calculated the force, we can use Newton's law of universal gravitation that relates force, mass, and distance to find the mass of a black hole. We can rearrange it as I showed to do this, and since we are given the position of both objects, the mass of the star and the gravity constant, and we just solved for force, we can plug all of that information in to get the mass of the black hole. And here is how I did that in Python. And here are my results. I estimated the magnitude of the net force is 9.6 times 10 to the 28th newtons. I also have the parallel and perpendicular components shown. And I estimated the mass of the black hole is 1.6 times 10 to the 34th kilograms, or about 8,000 times the mass of Earth's sun. And our first discussion question is asking how the net force and its parallel and perpendicular components are different from dp dt and its parallel and perpendicular components. So while the magnitude of our change in momentum over the change in time is the same as the magnitude of the net force, the difference lies in their direction. The net force is always pointed inwards towards the center of the black hole, but since the momentum is based on the instantaneous velocity of the star, the parallel component of the momentum principle is perpendicular to F net, while only the perpendicular component of the momentum is pointed inwards. And here is once again another model. You can see that the force of gravity is pointed inwards towards the center of the black hole, and so is the perpendicular component of the force, while the parallel component of the force is still tangent to the path of the star and is at a 90-degree angle to the force of gravity. And our second discussion question is, What if the black hole whose mass we found was removed and a different black hole is placed in the same location, and the motion of the observed star remains unchanged? Could you tell the difference? Is it possible to find a value for the mass that is different from our original? So if the new black hole did not change the path or the velocity of the star orbiting it, then my value of mass that I find for it would be the same as my original black hole. I determine the mass of the black hole using only the motion and mass of the star, so if none of those change, then the mass of, or the force exerted by the black hole that I found would not change either. So, in conclusion, because there was no experimental data, there is no difference between the observable data and the model I created. Overall, there's nothing I could really improve upon in the future, because this is reliant purely on the GlowScript model I was provided and basic physics principles, not any experiments I could have made mistakes while performing. Thank you for grading.